What if I told you Python doesn't actually have a built-in array, yet arrays are everywhere in Python code? In this tutorial, I'll show you exactly what Python gives you instead, and how to master all three forms of arrays from scratch, right up to advanced tricks used in real projects. We'll cover lists, the array module, and NumPy arrays, so you'll know exactly which tool to use for every situation. Before touching any code, let's build the mental model. An array is like a numbered row of storage boxes. Each box holds one value, and every box has an address, its index, starting from 0. This structure lets you store many related values under one variable name, access any value instantly, using its index, and loop over all values systematically. Watch as the highlight moves through each element, showing you how Python tracks position. Python gives you 3 ways to work with arrays, and each has a different purpose. Lists are built in and perfect for general-purpose work with mixed data types. The array module from the standard library gives you memory-efficient numeric storage, and NumPy arrays from the third-party NumPy package are the powerhouse for math, science, and data analysis. We'll cover all 3, so choose the right tool for your use case. Lists are your daily array workhorse in Python. They use square brackets with commas between items. You can create a list of numbers like daily step counts, a list of strings like city names, or an empty list that you'll fill later. Remember, square brackets create lists, not parentheses. This simple syntax is the foundation for everything we'll cover next. Use square brackets with an index number to access any element in a list. Positive indices count from the start, so 0 is the first element. But here's the trick. Negative indices count from the end, so -1 is the last element, -2 is second to last, and so on. This means you can access the end of a list without knowing its length, which is incredibly useful in real code. Slicing extracts a portion of a list using the syntax list start: stop: step. The stop index is never included, so 1 to 4 gives you indices 1, 2, and 3. Leave the start empty to begin from the beginning. Leave the stop empty to go to the end. Use a step of 2 to get every other item, or -1 to reverse the entire list instantly. Lists are mutable, meaning you can change them in place without creating a new list. Use assignment to modify individual elements by index, or assign to a slice to replace multiple elements at once. This mutability is both powerful and something to be careful about, which we'll see in the copying section. Python lists have built-in methods for adding and removing items. Use append to add to the end, insert to add at a specific position, remove to delete by value, and pop to remove by index and get the value back. Pop with no argument removes the last item. Pop with an index removes that specific item. These methods modify the list in place and are essential for dynamic data manipulation. Use the len function to get the number of items in a list. This is crucial for loops and bounds checking. Remember, the last valid index is len of list -1, because indexing starts at 0. This off by 1 detail trips up beginners constantly, so keep it in mind. Use dotAsir to modify a list in place, or the sorted function to create a new sorted list without changing the original. Both accept a reverse parameter to sort in descending order. The key difference is mutability. .sort changes the list you call it on, so while sorted returns a brand new list and leaves the original alone. Use a for loop to iterate over every element in a list. The syntax is for item in list, and Python automatically handles the iteration. When you need both the index and the value, use enumerate, which is the clean Pythonic way. It returns pairs of index and value, so you can unpack them directly in your loop. Here's a critical gotcha. Using b equals a does not copy the list. It creates a second reference to the same list. Changes to b will affect a because they point to the same object in memory. To actually copy, use slicing with a colon, the .copy method, or the list constructor. These create independent copies, so modifications don't affect the original. The standard array module creates arrays restricted to a single data type. You specify the type with a code letter, I for signed integer, F for float, D for double precision. This type restriction is what makes arrays more memory efficient than lists, because Python doesn't need to store type information for each element. Use arrays when you have large sequences of numbers and want to reduce memory without third-party libraries. Let's look at the numbers. Storing 10,000 integers in a list uses about 87,000 bytes. The same data in an array uses only about 40,000 bytes, roughly half the memory. This efficiency comes from storing raw numeric values instead of Python objects. For large datasets, this difference matters significantly. NumPy's NumArray is the powerhouse for anything involving math, data science, or numerical computing. Install it with pip install NumPy. NumPy provides creation functions like array from a list, arrange for ranges, zeros and ones for pre-filled arrays, and linspans for evenly spaced values. These are the building blocks for scientific computing in Python. This is NumPy's superpower. Apply mathematical operations to entire arrays at once without writing any loops. Multiply every element by a constant. Add two arrays element-wise, or apply complex formulas. This vectorization is not just convenient, it's dramatically faster than Python loops because the heavy lifting happens in optimized C code underneath. NumPy provides built-in functions to compute statistics instantly. Sum adds all elements. Mean calculates the average, max and min find extremes, and std computes standard deviation. These functions work on arrays of any size, making data analysis straightforward and efficient. Boolean filtering is incredibly useful for data selection. Create a mask by applying a condition to the array, which returns true or false for each element. Use this mask to index the original array and get only the matching elements. You can even combine the steps into one line for concise, readable code. NumPy excels at multi-dimensional arrays. Create a two-dimensional array by passing a list of lists. Access elements with row, column notation, entire rows with row colon, or entire columns with colon, column. The shape property tells you the dimensions. This is essential for image processing, machine learning, and any work with grids or matrices. List comprehensions are a compact Pythonic way to build lists. Instead of a multi-line for looped with append, write the entire thing in one elegant line. The syntax is expression for variable in iterable. Add a condition at the end to filter elements. Comprehensions are faster than loops and more readable once you get used to them. Create two-dimensional grids by nesting lists. Access elements with double indexing. Board row square bracket, column square bracket. Iterate through rows with a for loop, then through elements in each row. This pattern is perfect for games like tic-tac-toe, spreadsheets, or any grid-based data structure. Flatten a nested list using a comprehension with two for clauses. The pattern is item for sublist and nested for item in sublist. This reads almost like English. For each sublist in the nested list, for each item in that sublist, collect the item. The result is a single flat list containing all elements. The zip function pairs elements from multiple lists together. Iterate over the result to process related data side by side. Zip also works beautifully with dict to create dictionaries from two parallel lists. This is cleaner than manual indexing and less error-prone. Lists can implement stack and queue patterns. Use append and pop for a stack, last in, first out. For a queue, first in, first out, use collections dequeue instead of a plain list. Dequeue has poplift, which is efficient, while list pop of 0 is slow. Choose the right tool for the pattern you need. Here's your decision tree. Use lists for general purpose work, especially with mixed types or strings. Use array.array for large numeric sequences when you need memory efficiency without extra dependencies. Use NumPy for anything involving math, statistics, or data analysis. Use dequeue for queue operations. The right choice makes your code faster and more maintainable. Let's put it all together with a great analyzer. We take student names in a list and scores in another list. Convert scores to a NumPy array for efficient computation. Use zip to pair names with scores. Apply a pass-fail threshold, and use NumPy's aggregation functions to compute class statistics. This single example uses lists, NumPy arrays, zip, conditionals, and statistics, everything we've covered in this tutorial. You now know the 3 flavors of arrays Python gives you, when to use each one, and advanced patterns like list comprehensions, two-dimensional grids, zip, and Boolean filtering. The best way to cement this is to build something. Try modifying the Grade Analyzer project, or start your own. If this helped, like and subscribe. Next up, we're covering dictionaries and sets.